All right, good morning, everyone. Today is the second day of our three-series workshop talking about the Staff Consulting Center services that we provide. Today we'll go over briefly the different type of population and sample data that you may encounter in your research. Methods for gathering sample data. The session will conclude with a brief description of the basic statistical tests that we do at the consulting center. Some of these tests include t-tests, ANOVA, pair t-tests, independent t-tests. So I will ask Rabina to come forward and start. Thank you.
Thank you, Professor. So we are going to talk about population versus sample. So in statistics, population is the entire group of data that we are going to use to do some statistical test. It can be a group of individual or set of items, anything, and a sample is a specific group from that population. So it is a smaller and more manageable representation of the population, and it holds the characteristics of the population. Next slide. So we have this as the example of the population, or we can take the students of whole statistical department as the population and students taking Stat 103 as the sample. So next one, I'd like to ask Eddie to talk about this.
All right, thank you so much, Rabina. So this is an image showing us how we sample data from a variety of observations. On this screen, we have the population size, which is the number of observations that are presented to us through survey results. And then we have the sampling methods, which is done using a confidence interval of either 95% or 99%. And then we have a margin of error, which allows us to track any errors in our sampling methods. So usually we use a 5% margin of error because it's paired with our alpha level or a significance level of 5%. And usually we require that when clients send us their survey data, they have observations above 100. Because when the observations are less than 100, it's kind of difficult for us to sample the data from those observations. I did not put this on this slide, but before I drafted this whole image, I saw that if we had a survey with 30 observations, the only way we can sample the data using a 5% margin of error is 28 observations. So that means that there were only 2 observations that were not significant to the research. So looking over here, if our survey had 100 observations and we used a 5% margin of error, we will have 80 observations to use for our statistical tests. So as you can see, there is a wide difference of 2 when we use a population size of 100 versus if we use a population size of 30. And when we look here, if we have 10,000 observations using a 5% margin of error, we'll get 370 observations. So this is how we sample the data for our statistical tests so that our statistical results are accurate to our customers who use them for further research and further dissertations. And with that being said, I'll hand it over to Rabina to touch more on descriptive statistics.
Thank you, Eddie. So now we are talking about descriptive statistics. This simply describes or summarizes the characteristics of data that we are using in our test. So we have mean, median, mode, that is the measure of central tendency. So this describes the center of the data. We have standard deviation and variation, that is the measure of dispersion. This describes the dispersion of data within the test, and we have frequency tables that describes the occurrence of data in the test, and we can also describe the characteristics of data using graphs and two-way tables. Next one is we have hypothesis testing. So it is a type of statistical analysis that we do assumption on the data. So these are the general steps on how we can determine the probability that a given hypothesis is true. So first we state the hypothesis, and then we decide on the sample size and level of significance, that is alpha. After deciding this, we compute the test statistics on the data, and then we interpret the result, apply decision rules, and we conclude and interpret the result. After that, we have two types of hypothesis testing. They are null hypothesis and alternative hypothesis. Null hypothesis states that there is no chance of occurrence of the data. So we denote the null hypothesis using H naught, and alternative hypothesis is logical opposite of null hypothesis. So if we accept the alternative hypothesis, that follows the rejection of null hypothesis. So we represent it using H1. So I'd like to ask Eddie to talk more on alpha and hypothesis testing.
Okay, thank you so much, Rabina. So one way we can test if a model or its coefficients are significant is by using something called an alpha. So alpha is important in our decision criteria because it allows us to determine if something is statistically significant or valid, and if it's unlikely to have occurred by chance. So here we have three variants or three significant levels that we use to measure if something is statistically significant or not. So here is our p-value, which we call alpha, which we compare to our alpha, sorry. So our p-value, if our p-value is less than 10%, then we'll say we are 90% confident in the decision to reject our null hypothesis and conclude with the alternative hypothesis. And the same goes with 5%, which is the most common. So if we use a p-value less than 0.05 or less than 5% significance level, then we'll say we are 95% confident in our decision to reject 8 nodes and conclude with HA, which is the alternative hypothesis. In earlier slides, Rabina said that the goal of hypothesis testing is to reject the null hypothesis, because that's the only way we can tell if a statement is true or not, because it helps us in our decision criteria for running subsequent tests. And if our p-value is less than 1%, then we say we are 99% confident in our decision to reject the null hypothesis and conclude with the alternative hypothesis. And if you notice, the confidence level, the alpha is, if the alpha is 1%, the confidence will be 100 minus the alpha. So that's how we get the confidence level. So if our p-value, if you compare our p-value to our alpha of 1%, the confidence level will be 99%. Here is a graphical representation of how we use a one-tailed test to reject our null hypothesis for alpha. So over here, we have a bell-shaped curve where we have the acceptance region, which is the region of acceptance. And then we have either the left side or the right side. But for this graphical representation, we are using the left side as a rejection criteria. Now, I'm going to switch over to the board and tell you how we use this bell curve to reject our null hypothesis using our alpha. So if you could give me a moment. So I'm going to stop sharing here and then switch it to the board. So stop sharing.
And then that's fine, they'll see it.
Okay. So this is the board. That's where I'm going to describe how we use a one-tailed test to reject the null hypothesis using alpha. So if we have our null hypothesis that states that H node, we denote our null hypothesis by H node. And let's say that the mean, which is mu, is less than or equal to 5, right? So if this is our null hypothesis, HA will be the opposite of this, which will be mu is greater than 5. So we are going to use that graphical representation to detect if we should reject the decision criteria that mu is less than or equal to 5, or whether we should reject the alternative hypothesis that mu is greater than 5. So using this bell curve over here, we have the acceptance region. This is the positive critical value, if you can see here. And then we have the negative critical value. And so since this is our acceptance region, the rejection region will be the opposite of what is on here. So this will be to the left side. And the only way we can detect if we should accept or reject the null hypothesis is by using a T distribution table or a Z distribution table. So based on the T distribution table or Z distribution table values, we can determine if the p-value or the statistical value is valid enough for us to reject the null hypothesis and accept the alternative hypothesis, or vice versa. So this is a graphical example of how we use the 1 till t-test curve to reject using this criteria. And with that being said, I'll switch over to the presentation. Sharing. Okay, so. Okay, so this is our two-tailed test. So with a two-tailed rejection criteria, we have 2 rejection regions. And with this bell curve, it tells us, I'm going to show it on the board how we use the null and alternative hypothesis to reject both regions. So I'm going to switch over to my screen again so you can see the board. All right. So we are using the same bell curve again. And this time we have 2 rejection regions. So the only way that we can detect if the rejection is on either side of the bell curve is based on our hypothesis. So in order for us to have 2 rejection regions, our H node must have this criteria: mu is equal to 5, right? So if H node states that mu is equal to 5, then H A will say that mu is not equal to 5 because the alternative hypothesis has to be the opposite of the null hypothesis. So we have HA states that mu is not equal to 5. Let me write that better. So HA, which states that mu is not equal to 5, could mean that the mean can either be greater than 5 or it can be less than 5 based on our T values or our Z values. So this is an example of how we reject or accept the null hypothesis based on a two-tailed test, where the rejection criteria is on both sides of the curve. And with that being said, I will to Dr. Sumari to touch more on t-tests.
Thank you very much, Eddie and Ravina. So after once I've decided on their research they've done their homework. Basically, they came to us, we help them either collect data set through a survey, or they have a secondary data set, we help them clean that data set. They have questions that they have asked. They have stated their hypothesis. The next step is to go and do the data analysis, right? Because we need to answer those hypotheses, whether we reject or fail to reject them. There are many tests that are available depending on the situation. The most common ones are t-tests and ANOVA. You also hear a lot about chi-square tests, correlation, etc. But today we'll just focus on t-tests and ANOVA. And t-tests, we have two types of t-tests. The one is paired and the other one is two sample independent. So we have one sample t-test, we have paired t-test, and then we have independent t-test. So the example you have on the board is an output from JMP or SPSS. And this is discussing the case of a paired sample t-test. So an example of paired sample t-test, suppose that we come up with a formula that help with weight loss. So we collected weights of individuals before we gave them the formula, and then we collect the weight after they took the formula. That's an example of a paired sample t-test. So the choice of the test depends on the scenario that we have on hand, and we can easily help you determine what test you need for your specific project. So the null and alternative hypothesis discussed by Rabina and Adi previously. Here, we would like to see if the mean before and after are the same or different, right? So here, H naught mu1 equals to mu2, and H alternative mu1 different from mu2. So because we have in our alternative hypothesis mu1 different from mu2, that's an indication of a two-tailed test, right? Two-tailed test. Our significance that you have here, where it says if significant greater than alpha, if significant less than alpha, that's just our alpha level that we chose prior to making to the test. And alpha can have, we have three most common levels for alpha that we choose most of the time. The most popular is 5%, 0.05. But we can also have 10%, we can have 1% depending on the specific field of study. For this example, we'll look at specifically the pair three. So we are comparing different pairs here. You can see in the table you have a simple descriptive statistic. The top table toward the right of the screen. You can see pair one, pair two, pair three. So we'll focus on pair three here. So pair three is comparing knowledge tests prior and after giving a certain treatment, right? So there should be a way that they will collect the knowledge before people go through the treatment, and then after they taking the treatment, then we collect again. We do a test again. We collect the answers, and then you can see we summarize it by their mean, standard deviation, and standard error. Now down here we get the result of the statistical analysis, right? So we can see for pair three we have the mean, we have the standard deviation, standard error. And on the other side, we have the 95% confidence interval of the difference. So this is the difference between the mean before and the mean after. And we have that difference here. And then we have the lower and upper limit of the confidence interval for that difference, where that difference might fall if we took many samples of that kind. And we have the test statistic t-test. Now, there is a specific formula behind how to compute a test statistic for a paired sample t-test. But because we're using a software, the software does it for us in the background, but it's beneficial as a researcher to know how those is computed if you're interested. But most people won't necessarily, but it's good to know sometimes, right? And then here for SPSS output, you'll see that at the top of that last column, the label says significance in parentheses two-tailed. It indicates the kind of test that we are doing here, right? So as I said, our alternative is looking at if the mean before and the mean after are different, and that's just a two-tailed test, So out of this table, our first concern will be looking at what our test statistic looks like and what's the rejection region, right? Of course, we have to verify if all the assumptions for such a test is met, right? So that's what we pulled here, where it says pair 3 here. So t equals to minus 6.57, that's your test statistics score. The next thing is to see if that's significant. So the word significant just means that if we have evidence that there is a significant difference between the pre and the post, right? So the p less than 0.001, if you remember the slide, the previous slide, Eddie was showing on the alpha slide, where he was comparing p to alpha. So this p less than 0.001, here your p-value from the table was 0.00. It's just saying it's just 0. I mean, very small. So, and then we say this p-value is less than 0.001. If we choose an alpha level of 0.5, of course, that p level is less than 0.5 already, right? So this is a highly significant test. So we can conclude. So now we can briefly conclude in a few sentences, the whole test statistic that we have conducted here. We can reject the null hypothesis based on this information because we saw that it's significantly different from 0. So we can reject the null hypothesis and say there is a significant difference between the pre and post tests. And in parentheses, we give T36. So the T is an indication that that was a t-test, and T represents the test statistics score. And the parentheses 36 is just the degree of freedom of the test, which is the number of observations here that we have, or you can see here, we have 37 observations and then -1. And then it gives you that test statistic, which is minus 6.57, and the p-values that goes with it. Those are the pair of numbers that are important. And then on the other side, because we are interested in the post-test, because we want to see the effect of the treatment on the knowledge, right? And how different that is from before taking the treatment. Then we say the post-test, and we give the mean of the post-test, which is 8.62, and we can see that mean is way high than the pre-test. So there is a significant increase in knowledge. Whatever that treatment is, cause a significant increase in knowledge. So we show that, and we give the standard deviation was significantly higher than the pre-test with the mean of 6.59 and standard deviation. And that, if our research was about proving that a certain treatment will induce a higher knowledge in people or in any other subject, then we have concluded our research in that case, right? So that was an example of a paired t-test. Now, there are cases where we'll have independent groups. Independent groups, so the data is collected independently from two groups, and we are comparing across the groups, right? And so the setup is the same. Let me give you an example of an independent group. So we're looking at income earned across let's say male and female, right? Trying to compare if they are equally the same income. So, and then here the setup is the same. It's just the procedure is a little different because of this is independent versus that was a pair t-test, right? So null hypothesis, there is no difference. So the null hypothesis is always a statistical. We assume there's no effect, there's no difference, it's all the same, right? So there's no difference between male and female. So in my example here, so we can see gender, male and female, and then M1 equals to M2. Our alternative here, again, this is an example of a two-tail, right? Alternatively, we can see, oh, maybe there is a difference, or we believe there is a difference, because the alternative is what prompts the whole research, right? So we believe there is a difference, and we would like to assess that difference, right? So alternatively, the mu1 is different from mu2. Now, what's important here to note when it comes to two-sample independent group t-test is there are two formulas in computing the test. One assumes equal variance, and the way we compute that is different, and the other one assumes unequal variance, and the way we compute the test is also different, right? The software will give you both. One would just be wrong, right? So the software will use the formula assuming equal variance and compute the test. And the software will also use the formula for not assuming equal variance and compute the test for you. One will be wrong, and it's our duty to check which one is correct, right? So the first thing we need to do before we compute our two sample t-tests, independent group, is to check if they have equal variance. And we use Levene's test to do that. So Levene's test for equality of variance decision. If once we compute our Levene's test, if the significant value, which is the p-value from that test, so Levene's test says the variance in group 1 is the same as the variance in group 2, and the alternative, they are different, right? So we get the p-value for that as well. So if the p-value is greater than the chosen alpha, again, we'll just go with 5% in general. For Levene's test, that's an indication that we should assume equal variance. If the p-value is less than alpha, less or equal to alpha, let's suppose 0.05 again, that means we should not assume equal variance. So once we've decided on whether it's equal or not equal variance, now we can go ahead and look at the output that we obtained from our software regarding the test statistic. So up here, we will always accompany our data analysis with a brief summary statistic. So up here we have a summary statistic of our data set. So we have the categories, male and female, we have the number in each. One thing to notice here is we have 26 and 9. So this data is not balanced at all, right? So that's one thing to notice. And it's good to always try to balance the data set in all groups. And then we have the mean, we have the standard deviation, we have the standard error. So down here, we can see the output of the independent t-test. One side of it here, we can see the Levene's test for equality of variance. We can see the output, that's 0.07. And then how we use that to conclude. So the other side, we can see the t-test for equality of mean. So not to confuse. So this side is comparing the variance. The other quadrant is looking at the test statistic itself. So testing our hypothesis. So just like previously, we'll look at here, we'll look at the test statistic, and then we'll look at the p-value, that significance two-tail. Now, because the Levene's test was less than alpha, because the Levene's test is 0.007. And that value, 0.007, is less than 0.05, right? So because of that, we will have to not assume equal variance. And that's kind of intuitive because already we know that the data is not balanced. We have 26/9. We can expect the same variation, right? So sometimes it makes sense. So because we are not assuming equal variance, we have to focus on the line that says equal variance not assumed. So that's the second line in our table. Because they're all saying the same thing, just one is saying equal variance assumed, the other one is saying equal variance not assumed. So equal variance not assumed, and then I'll go in that line and I'll look for the t-test for my test statistic and the significance value. So the t-test here for my test statistic is 1.257, and the significance is the one here, you can see 0.238, right? So I'll pull that out clearly, and that's what we have here. So we have t 9.69, and then we have p-values that is given here. So that 9.69 again in parentheses, just like previously, that represents a degree of freedom. Now, for two independent groups, and specifically when it's unbalanced, there is a specific way to compute that degree of freedom. Right? The software will handle that for you, but it's good to know how that is computed so you know the logic behind it as well. And then so you have the t-statistic, that's your test score, and then you have your p-value, which is 0.238. And then what we need to do here is to compare that p-value to our significance level. If we chose a significance level of 0.5 or 5% or 0.05, so this value, this p-value that we obtain from this step is way higher than that, right? So 0.23 is greater than 0.05, and in this case, what do? We fail to reject our null hypothesis. So we couldn't establish. So once we need statistic, we don't merely say that we accept the null hypothesis, right? We say there is no evidence, there is not enough evidence. We couldn't establish that the null was false, right? So we failed to reject the null, right? So we couldn't establish that there is a difference between M1 and M2 for this test here, right? So basically, that gives you an idea of what t-tests work, and we can go more in detail in our consulting center. The other type of test that you will see a lot, most commonly used in the field, is ANOVA. All right, so ANOVA compares. ANOVA is also known as analysis of variance. Right, it compares two or more groups. When you have, suppose I'm trying to compare the income across group age groups or across ethnicities, right? So we have multiple groups in there. So t-test is just two groups, period, right? So ANOVA can take more than that. So what ANOVA does is, before we even think or spend our time and compare all possible pairs, let's check if overall, there is the difference across the groups, right? So we use the F statistic to do that. So your null hypothesis is all the groups are the same, all of them. So if I'm looking at race, for example, all the categories, right, all the race, when it comes to income, they're all the same. That's what the null will assume. The alternative is trying to say that at least one race has different income than the others, right? So I know what will save you time if indeed they were all the same. Because before you detect which one is different from which one, you will have to do a lot of multiple comparisons, right? So once we have this, we test, we use the F statistic that looks at the variation between the groups over the variation within the group. So that's what the F statistic stands for. So let's look at a specific example here. One way ANOVA between subject, right? So up here we are comparing the groups, and we have these three groups here. So trial 1, trial 2, trial 3. And up here, well, down here is the descriptive statistic. So we have the mean of the first trial, we have the standard deviation, standard error, we have the confidence interval, we have the minimum and the maximum for each of these trials, right? So you can see what the data looks like. And let's say we are interested in see if the mean of the 3 trials are the same or if they're different, right? And then to ANOVA, we state our hypothesis. We say mu1 equals to mu2 equals to mu3, and our alternative, at least the mean of one of the trials is different from the others. So up here, go back to the previous slide. So up here you have the output of the ANOVA. So you see the between groups, you have the within groups value, and then you have the total. And then all the way, for this table, what we are interested in is the F statistic, right? So your F statistic, if you look at the formula, it says is a variation between over the variation within, right? So basically the between groups, so this mean square here represent the variation between. This one here represent the variation within, which is also known as your standard error, right? So you take this over this, that will give you your F statistic over here. And then the last column is your significance. So we are focusing on these two numbers here. So this F is my test statistic for the ANOVA, and then this significance here is the p-value. Now, because my p-value, it says 0.000, right? It's less than 0.001. So this is significant, which means that we rejected the null hypothesis. We have evidence that the null hypothesis is rejected. that means that one of these means or all of them are different from each other. That's what that indicates. We might be interested in knowing which one is different from which one, right? So then we have to take an extra steps here, and that is known as a post hoc analysis. So in a post hoc analysis, we'll look at all possible pairs that we can get from the three groups. So the first pair is to look at trial 1 and trial 2, trial 1 and trial 3, and then trial 2 and trial 1, trial 2 and trial 3, and then trial 3 and trial 1, trial 3 and trial 2. Those are the possible pairs that we can get. And what we're trying to investigate here is to see which pairs are different from which ones, right? And then we use the Tukey HSD to do that. So the Tukey HSD, you know how we said we used the t-test previously to find our significance level. Here we use a Tukey HSD. So here, this will be done for you automatically by the software when you chose that option. But it's always good to know how it works on behind, right? So then here we are interested in our significance here, where it says significance here. So this will give you the mean difference between the pair. It will give you the standard error, it will give you the significance, and then will give you your confidence interval. As Eddie discussed, right? So confidence, you know, if I'm 5%, if my significance is 5%, my confidence is 95%. And the confidence interval gives you the range where that difference will fall within. So then we look at this significance, and what we are trying to look for is which of these pairs are significantly different from each other. So the first one, 0.16, is not significantly different because that's just more than 0.5. 0.05, this is significantly different. So that pair is trial 1 compared to trial 3. It shows that those two are different significantly. And then we go down the list, we see another one. That's trial 2, trial 3. Those ones are significantly different. And we see the other two, right? So trial 2 and trial 3, and then trial 3 and trial 2. So now, the test will give you all that, but then you have to realize that trial 2, trial 3 is the same as trial 3, trial 2. Right? So it's just one. And then you go back here, you look at trial 1, trial 3, right? So trial 3, trial 1 is the same. So at the end of the day, the ones that are significantly different are trial 3 with the mean of 7.51, standard deviation of 1.6, that was significantly higher than both trial 1 that with the mean of 2.98 and trial 2 with the mean of 3.64. So trial 1 did not differ from trial 2. So that's how we handle the post-hoc ANOVA. And this is just a glance of the possibilities, and there are many more other tests depending on your specific situation. Thank you, and I'll pass it on to the next presenter.
Thank you so much, Dr. Sumari, for touching on so many of the statistical tests that we run at our center. So I created this summary table to kind of summarize everything that Dr. Sumari talked about. So in this table, we have an independent variable column, a dependent variable column, and the methodology for this. So let me just define what an independent variable is. So an independent variable is a variable that we use to predict an outcome. So let's say, for example, we want to predict how a company increases wages for its employees at 3M, for example. Some possible independent variables are the experience of the employee, the profitability of the employee, as in the revenues that they make. It could also be the resources that they avail to employees on a monthly or a yearly basis. It could also be benefits or sponsorships that they get from other donors, so on and so forth. So the independent variables, all those factors will be used to predict if the wages will increase for a particular employee or not. And the dependent variable in that whole description is the wages, of course. So let's start with the first row. So if our independent variable is categorical, that means it's, let's say, for instance, we have gender. A gender is a categorical variable because it has two terms. It has male and female. And then we have a numerical dependent variable, which is all numbers and it's continuous. Then our methodology will be ANOVA, right? So as Dr. Sumaris said in the previous slide when he was explaining what ANOVA is all about, the independent variable and dependent variable comprises of a lot of factors. It doesn't just boil down to one or two factors. Then we'll go to the second column. If our independent variable is one numerical variable and our dependent variable, which is our predicting variable, our predicted variable is one categorical, then we'll use one-way ANOVA. And in our final column, if our independent variable is two categorical, and by two categorical, it means it could be binary. So let's say, for instance, we have male and female as an independent variable. Our one could be denoted as one, and then the other could be denoted as two. So for instance, if we wanted to determine how, if the salaries between males and females are equal, and we have gender as both male and female, right? We can denote male as one and we can denote female as two. And when we run regression analysis, we use a lot of dummy variables or binary variables. And so there are instances where you have two categories, where you have male and female. And so we will have to create a dummy variable where we denote one variable by one and another variable by two, just so we can see how those variables affect the predicted variable. So if our independent variable is two categorical, male and female, and our dependent variable is numerical, let's say income, then our methodology will be t-test, because we just want to measure if there are equal variances or if the means are the same. So with that being said, that summarizes our entire presentation, and I will leave this session for any questions that any of our attendants have. We'll be willing to answer them.
Thank you very much, Eddie. Thank you very much for your time. We really appreciate it. I think we're going to be 10 minutes over. So, and if you have any questions, please feel free to ask.
So let's go to this one. Let's do this.
I go back.
Yeah, it's loading. This one?
No, back. Like three slides before.
Okay. It wasn't. Oh. The next one. Oh, you said,
Oh no,
This one.
the next one.
the next one.
Okay.
Yeah, this one. Is the Leibniz test for equality of variance decision the only possible test? Or
No,
there are different
no.
types?
No, that's a good question. We have other tests. Leibniz test is widely used, but we definitely have other tests that you can use for equality of variance.
Okay, so why do we look at the variances over the standard deviations?
Why do we, oh, if you compare variance, is the same as comparing the standard deviation, basically. It's the square root variance, standard deviation is the square root of the variance. So these are two positive numbers, all right? So if I compare 2 to 8, square root of 2 to square root of 8 will be the same comparison, basically.
Okay, and also talking about one-way ANOVAs, you talked about post hocs.
Yeah, post
Talked about with Turkey. Is there any other post hoc tests?
They are, in fact, they have, we have others. The reason when you do multiple comparisons, we have to find a way to control for multiple testing, and there are multiple ways for doing that. We have done it, is one of them. Any other questions? We can stop here. Dr. Melanie, do you have anything in it?